Welcome to the next session. In this session, the topic is a recent call from Digital Futures. It was a new call, I think, the first time from this year, called Societal Innovation Projects. My name is Lainey Gutierrez-Fairwick. I'm a professor here at KTH in Stockholm. So the background of these societal innovation projects is that this type of project should bring together partners from the academic, industrial, and public spaces, what they're calling a triple helix model of innovation, to define a promising scope of introducing digital technologies in the public sector and demonstrate a path towards wide-scale adoption in the triple helix constellation. For this first round of calls, there were two groups that were awarded, and we are both here. I first introduce my colleague from Stockholm University, Erik Per Jons, who will present his project called System Support for Online Rehabilitation of COVID-19 Patients. So first, thank you, Erik, welcome.
Thank you, and I will now share my screen. And you will now see the presentation in front of you. As Elena mentioned, the name of the project is System Support for Online Rehabilitation of COVID-19 Patients. And in the project, I have a colleague, Martin Henkel, and we are both docents, coming from the Department of Computer and System Sciences. The background to the project is that there is a large number of patients with severe cognitive problems after COVID-19. They could have concentration problems, they could be tired, or they could have memory disorders. The rehabilitation clinics are overwhelmed with such patients, and the waiting lists are long. Therefore, an online rehabilitation training system could be a useful solution in order to support both patient and the clinicians. So therefore, the aim of this project is to develop a system for online rehabilitation of patients with cognitive long-term symptoms after COVID-19. And these systems should help the patient to understand more about their symptoms, train to overcome these symptoms, and also to increase their motivation to work with rehabilitation online. So you can say that this system is a kind of support self-care, although there will be online coaches that also will interact with the patient in this system. The project's duration is 2 years. It started late August. And the partner in this triple helix project are the Danderyd Hospital, their rehabilitation medicine university clinics, Stockholm University, and a company called Visera Integration, and Telia Company. And Telia Company work as a reference partner. And the project is funded by Digital Futures. This project is based on 2 previous pilots that has been done, where a system has been tested on patients and clinicians, and they've been positive to such a system, but they want additional functionality. For example, a patient wants to follow their own development, so they can see how they will improve their cognitive abilities. The patient also wants to get support from an online coach, according to an investigation done in these 2 pilots. Clinician, on the other hand, wants a module-based individual adaptation solution, so they could, so to say, could change the training for individual patients. So that should be easy. And the clinician also want better follow-ups of result on the online rehabilitation, so they can learn and improve their way of handling the patients. The system to be developed, the online rehabilitation training system, must be able to run on various platforms, since today people are used to work on different types of systems like smartphones, iPads, and also ordinary computers. But in this system, we don't only want to create a system, training system, we also want that this system to support the whole rehabilitation process, and that this system should be integrated with existing system, for example, the patient journal system. So therefore, we also in this system introduce a new visualization technology by Visera integration. And this technology aims to support the design, the implementation, and the execution of healthcare processes. So the technology coordinates physical flows, manual workflows, automated workflows, and information flows. And also support integration of different types of systems. And Visera integration has long been working with integration and has also worked with creative systems supporting different kind of healthcare processes. The overall plan is that we, based on the existing pilot system, analyze and concretize the needs of the patient and clinics, and also including new interviews with the patient and the clinicians. A more advanced pilot system will then be developed for a larger test in clinical environment with 40 patients. And the test will include both the patient views, suggestion from the patient how to use, how to better use the rehabilitation system, as well as the clinician's assessment of the patient's improvement of the symptoms. And this will result in a final adjustment of the system. So the expected effects of this project will be improved rehabilitation for patients. They can start work earlier, decrease the workload on rehabilitation clinics, for example, saving the clinician with unnecessary work steps such as calling and reminding the patient of the rehabilitation, and better tracking of long-term effects on online training. Thank you. I will now stop sharing.
So, thank you very much. So the second presentation in this session is from me and my research group. I will share my screen now. So my colleagues at KTH and I here have been working on a project called Deep Camera-Based Movement Analysis for Remote Rehabilitation and Physical Therapy. I want to acknowledge my colleagues, Frederick Olson, a postdoc here, and then two former master's students, David Cecilia and Antea Destro. We are at the KTH Movability Lab at the Department of Engineering Mechanics. So once again, this is a brand new project for us, funded by Digital Futures Societal Innovation Projects. We were given a rather specific theme for this call. The theme should be in digital tools for remote rehabilitation. The triple helix that we use in our project is not unsimilar from Eric's. It's us here at KTH, partners in the public sector from Region Stockholm, more specifically the neurorehabilitation clinic at Danderyd Hospital, with, in this case, a little more focus on persons after a stroke or a brain injury. Colleagues there are Suzanne Palmkrantz and Christian Boy. And the industrial partners, a large telecom company in Sweden, Telia AB. This is a 1 to 2 year project, again, brand new for us. We just started in late August. Our overall goals are to complement current methods for remote rehabilitation with quantitative measurements of a patient's movement ability. And in our vision, we hope there's opportunities to promote live interaction and feedback between a patient and a therapist, and to measure and record longitudinal changes in movement function during this rehabilitation period. We here at KTH have had specific goals and a specific plan to measure movements using depth cameras that are pre-installed on iPhone 12 and iPad Pro models. This is my iPhone 12 and the LiDAR camera is right there. Okay, so LiDAR is one of these. There are other depth cameras, but as I mentioned, these already come pre-installed on the newer, little better units from Apple. So the way these things work, very briefly, is that they transmit light pulses constantly, and distance is detected in the field of view by recording the time between transmitted and backscattered pulses. So in this kind of technology, a topology of the camera's view is created practically in real time. And then Apple also has an AR kit that includes a human body model, which from this topological scan can then identify different body segments and joints and so on. Again, in essentially real time. So our plan and preliminary results, again, what we started and what we plan during the next few months are to create an app to capture human movement and upload this captured data in a meaningful and useful way. To technically validate Apple's human model, we want to validate this with a simultaneous capture from a 3D motion system, which we have just that ways. And then identify whether offsets and systematic errors exist and how we can compensate for them. Again, we want to correct or adjust Apple's model with data-driven methods. So I'm going to try to change and share a different screen right now. I'm going to share my iPad, which is sitting just on my desk next to me. And in here, I'm using an app that we did not create. This one's called Mobile Cap that we found on the App Store. Okay, so this is my iPad that's just next to me. And I'm going to give you a brief demo of how this looks. This is me. So this was just saved. And this is what Apple managed to put together from a live picture here. Oh, that was the wrong video. Let's try the right one now. Here we go. That was the one I just recorded a second ago. It goes a little crazy when I walked out of the view there. Okay, so I can show you a little bit of the validation study we've done in the past few weeks here. We have measured data from one subject who happens to look a lot like me in our 3D motion lab. In our motion lab, we have 10 Vicon cameras with high resolution and so on. We equipped me, in this case, with more than 50 passive markers, which the Vicon cameras can record, and from there it models joint centers and segment angles and so on. We can call this something like a gold standard in this branch. And we collected from 2 iPads at the same time. I did a few different kind of motion trials. First, I did very isolated motions, for instance, only left hip flexion or right knee flexion and so on. And then I did more complicated movements like walking and so on. So we've started to compare the 3D joint and segment movements from our motion capture and from Apple's AR kit. And from here, you can actually see a picture of the model that Apple can fit onto a person, live from these sensors. All right, so here you can see the avatar overlaid on top of me as I did some of these motions. Don't worry about the avatar's position. It just sort of appears on the screen there, but it does show how it's measuring me. Again, these are from the first set of trials where I did some isolated motion. On the plots I'm showing you here, on top I'm showing hip, and on the bottom I'm showing the knee flexion extension. And then on the left side is my left side and right side. Okay, so on the top you can see all of the motions I did, and on the bottom we've zoomed in to just one or two motions during that whole period. And in all of these, the golden standard, what's called the Vicon system, is shown in blue, and from the data from the iPad is shown in red. What I hope you can see here is the magnitudes don't really match all that well all the time, but they do sometimes, and the patterns are actually captured quite well. I'll show you another one here. This is when I stepped onto a treadmill. Again, it's hip on top, knee on the bottom, left and right, in the same color convention as before. So again, you can kind of see that the magnitudes sometimes match well and sometimes don't really match well. So we're trying to determine what that's all about, and if there's systematic offsets, they might be easier to adjust for. And if, things like certain camera angles make a difference, if we should move the iPad around for different motions and so on. This one I did some squats and other things. I'm going to move to the end where lunges were actually predicted quite well here. Lunges right there where I step out on with one leg. Those were tracked actually remarkably well, I think. So that's just a little bit of the preliminary data we've been able to measure so far. So what are future plans here? We at KTH plan to develop and validate, and if we have to, improve at the Apple models measured angles, and then to develop an app that can be used for an interactive clinical rehab visit in which motion, it can be measured live. Feedback from previous motion capture can be given, and results from earlier measurements, perhaps over a long period of time, can be discussed. What we're hoping for our clinical partners is that they discuss and create a list of relevant goals and movements that we should be aiming for, certain parameters we should follow up, and then we would like them to suggest a patient population for pilot testing. And our industrial partners, we hope can help us to plan or propose how a pilot test can be practically performed, and to help us with a protocol for secure data management and storage. So with that, I thank you for your attention, and Erik and I are both here to answer any questions you may have.